Hi, everybody. I'm Diane Greene. I run Google's Phenomenal Cloud. I'm on the board of Alphabet, and I'm incredibly proud today to be here moderating this panel of just absolute leading experts, leading researchers and experts in artificial intelligence and machine learning. We're going to structure our panel talking about past, present, and future, closing with some personal reflections on the industry and our careers. And before I do that, I'm just going to quickly introduce everybody. First is Françoise Buffet. She's principal scientist at Google and is the leader of speech recognition at Google, something everybody uses. Been at Google 12 years. Second is Fei-Fei Li. She's the chief scientist of Google Cloud, bringing AI and ML to companies all over the world. Also head of Stanford's AI Lab and inventor of ImageNet and the ImageNet Challenge, which really contributed to some of our developments in deep learning and AI. And she's also a champion of STEM and AI and the founder of AI for All. Next, Fernanda Viegas. She's a senior staff researcher at Google. She's a computational designer. She focuses on the scientific and collaborative aspects of information visualization, co-leads the Big Picture Data Visualization Group. She's part of Google Brain. And she's also known for her visualization-based artwork, which is part of the permanent collection of the Museum of Modern Art in New York. And then let me introduce Daphne Koller, who today is Chief Computing Officer at Calico Labs, which is a part of Alphabet, working to give people longer and healthier lives. But she's also, she spent 18 years at Stanford. She led the AI group there. She co-founded Coursera, which is the largest platform for MOOCs, massively online courses, open online courses. And you know, Daphne was one of Time Magazine's 100 most influential people in 2012. She won a MacArthur Foundation Award. She won the inaugural ACM Prize for Computing. She's a member of the Academy of Arts and Sciences, the Academy of Engineering, and those are just some of the proof points of her excellence. So we'll start with a historical perspective, and Daphne, as one of the most prominent and prolific authors of machine learning research papers, can you give us your perspective on how we've transitioned to deep learning?
So I think the deep learning revolution is a truly exciting enabler that we're seeing today in so many aspects of so many real-world problems. But that revolution came out of an outgrowth of a lot of machine learning research that led up to it. So prior to deep learning, there were probably about 10 or 15 years of very hard work in developing models that were maybe more handcrafted, that required a lot more thought and a lot more prior knowledge, and we really had to think through the specifics of the model and how it relates to the domain, because when you don't have a lot of data, you have to replace that with a lot of human intuition on how the model ought to be constructed. As we've gotten more and more data in certain domains, text and images being, I think, the two primary examples, and speech, of course, as well, we've started to replace a lot of that need for human insight with more and more data that counterbalances that. But the techniques that were developed in those 10 or 15 years are still pivotal today, both in the methods themselves, those optimization algorithms that were developed over the last 10 or 15 years are still a key component of what enables deep learning to be successful. And I think that while we might like to think that big data is at this point the solution to everything, it's a solution in certain domain areas, but in others, we still are unfortunately in the medium or sometimes even small data regime. And so there's still definitely a need for balancing human intuition with, about the domain with the data that we're acquiring and coming up with a model that incorporates the best of both.
Thank you. And Fei, can we also get your perspective? You're running the Stanford AI Lab. Your image network was seminal, and now you're looking at how bringing AI to every company in the world. What is going on with that transition?
Right. Thank you, Diane. So just a little bit of a historical perspective that AI in all sciences of human civilization is actually a very young field. We're about 60 years old. But the very question of the quest for intelligence, in my opinion, is what's at the root of AI's inspiration. And that dates back since the beginning of the dawn of civilization. So about 60 years ago, when machines start to compute and calculate at that time, very simple arithmetics. Already thinkers like Alan Turing challenged humanity with the question, can machines think? Can machines have intelligence? So about 60 years ago, leading computer scientists like Marvin Minsky, John McCarthy, and many others get together and really jump-started a field that today we know as AI. The AI that the founding fathers saw was very different technically 60 years ago, but it was the same core dreams, which is making machines to learn, to reason, to think, to perceive, to speak, to communicate. And AI has gone through several waves of technical development, from first-order logic to expert systems, to the early waves of machine learning, to today the deep learning revolution. I would say the past 60 years, I call it the in vitro AI, or AI in vitro. It's the 60 years there as a field, we laid the foundation of the questions we ask, the subfields that are essential to AI's quest, like robotics, computer vision, natural language processing, speech processing, combio, and so on. But also the way we measure the progress, to understand our data and discover the tool sets. So around 2010, around that time, thanks to the convergence of the maturing of statistical machine learning tools, the convergence of big data brought to us by the internet and by the sensors, and the convergence of computing, the Moore's law carried us to much better hardware. These three pillars came together and lifted AI from the in vitro stage into what I call the in vivo stage. AI in vivo is where AI is making a real impact to the world. It's just the beginning. Every single industry that at cloud, at Google, we see is going through a transformation because of data, because of AI and machine learning. And this is what I see as the historical moment that AI is going to impact and transform the field. But I also do want to say it's just the beginning. The tools and the technologies we have developed in the field of AI is really the first few drops of water in a vast ocean of what AI can do. We cannot over promise this. But there should be tremendous excitement that we can do a lot of more work to make this AI in vivo happen.
I share your excitement, this in vivo state. I mean, companies are putting virtual renditions of themselves in the cloud, and then they're using AI, to do things nobody ever thought was possible, and AI is being used everywhere. not just in the cloud. So thank you. If we dive a little deeper, Françoise, you've been at the frontier of speech recognition, and now in applications, speech recognition is actually becoming almost commonplace. Can you take us through that transition?
Yes, certainly. So I joined Google about 12 years ago, and a bunch of us came with this vision of doing something useful and fun with speech recognition. Speech recognition had been around for quite a while. All of us had some background in the field. But we wanted to do something fun. And that was hard because speech wasn't at the quality it is now. So we started with fairly limited products where the task of recognizing what the person says wasn't too complicated. We were just trying to push the envelope a little bit, but not too much, right? Because we needed to bring it to a place where the product was successful enough that people would want to use our application, and then we could start, folding data into the models and keep iterating from there. So we built what we called Goog 411. I don't know if any of you remembers that, but it was just a phone application. You would call a number, and then it would say, hey, what city and state? And you would say what you were interested in, and then it would ask you about the business that you were interested in. You would say that name, and then it would offer to connect you to that business in that city and state. So again, picture that. It's 12 years ago. There's no iPhone, no Android phone, right? All you have is that little flip phone that you put to your ear. So it was very basic. Fortunately, leadership at Google was really visionary about this technology and really encouraged us to push the boundaries as much as we could. And so we were successful with this first application, but then the iPhone and the Android phone came, so everything changed, obviously. Now there was visual feedback. So we started thinking about other applications, and that was voice search. So Google search by voice, and then we started doing dictation and having a little microphone in every possible entry point in your phone, so you could do everything with your voice. And more recently, we've moved into trying to enable speech recognition within your home with devices like Google Home. And because people are asking for more and more tasks to be fulfilled through voice, that was a really good entry point into the whole assistant story, where instead of just enabling you to do very small things with your voice, now you can ask questions, you can phrase them in natural language, you can get really Google to be your assistant without this cumbersome, physical keyboard input.
Thank you. Fernanda, you said you want to democratize data visualization. Now, and that's sort of inextricably linked to data. How did you get to that? What are the needs you see for data visualization, analytics, and how's that evolved?
Yeah. So I started working in data visualization over 10 years ago, and when I did, it was much different. It was much harder to do data visualization. The machines were not nearly as good. And there wasn't as much data out there that was publicly available. That started to change, and now we find ourselves in an environment where people are interacting with data visualization sort of everywhere. It's really exciting. It's been amazing to see journalism take on data visualization and talk about really complex stories. When they talk about statistics, we always joke that data visualization is sort of the gateway drug to statistics. It's like you're doing statistics without even noticing that you are, because we're just visually so good at picking up patterns and outliers and so forth. So data visualization has been on this trend of becoming more democratized, and also I really believe that we have been increasing people's ability to take in data and numeracy. And so data visualization has had a role to play in that. In terms of AI, it's been really interesting because we saw a major jump when Jeff Hinton and colleagues proposed the first sort of blockbuster visualization for AI, T-SNE. It's a technique that allows you to, so one of the big challenges with AI, with machine learning, is that these are systems that work in very high dimensional spaces. And those are really hard for us as humans to understand. So visualization is one way that you can sort of peek and try to understand what's happening in these systems. And these techniques, such as the one that Jeff Hinton developed, allow us to sort of understand how things are clustering together, what are the relationships between different concepts, and how these systems are sort of resolving the data that they are ingesting. So I'd say that was a major progress. And the beginning, as Fei was saying, I feel like we're also in the beginning of this relationship between how visualization can help AI.
Thank you. Now we're going to switch to a slightly more technical set of answers to what's going on in the present. Françoise, maybe we'll start with you and talking about speech recognition technologies and what have the transition been, and and what were the challenges and what are they today? How have the challenges evolved? Yeah.
Yeah, sure. Speech recognition is really complex, right? It's difficult to recognize what you're saying. Each one of us has a different voice, has a different accent. We're speaking in different environments, so all that contributes to the richness of the voice. And I think mostly for that reason, speech recognition has always been based on machine learning. There hasn't been, or not much of an earlier phase that wasn't machine learning based. It's just that the type of machine learning has been evolving over time. And we kept making progress in the field for the last 3 decades, but I think one inflection point has been the adoption of neural networks. And that has happened maybe 8 years ago or so, maybe a little bit less. But the early research in speech recognition using neural networks happened a long time before. There was a lot of activity in the field. There were a lot of promising results. However, there wasn't the compute support to really make it happen. And so neural nets were a little bit abandoned for a while, and speech recognition kept improving with more basic methods like Gaussian mixture models and whatnot. And then when we started really involving into deep neural nets, it was a big effort from an engineering viewpoint. We had to deal with latency issues, with size, with training capabilities, and so on. And eventually, when deep neural networks became a reality, when we launched them, when we really had them in production, that opened the path to a whole bunch of other improvements, because now we had the capability of having that complex machinery there behind the technology. And so we could move very quickly from one neural architecture to the next. And so we started looking into recurrent neural networks, such as LSTM. We looked into convolutional neural networks. And so CTC-based sequence modeling. We have a whole bunch of sequence modeling new implementations coming up. With Google Home, we have the neural beamforming. And so essentially what's happening is that the move into the neural network space has opened this incredible capability for innovating the core technology that powers our systems and keep optimizing and giving all of you in whichever language you're speaking the best possible accuracy we can.
Okay, well, neural nets for speech recognition to neural nets for extending our lives and making us healthier. A fairly open-ended question for you, Daphne. why does Calico need one of the top researchers in the world in molecular biology, biological computing, and also machine learning? As the chief computing officer, what are you doing over there?
So many of you may not know of Calico because we've been a little bit under the radar. So Calico is one of the Alphabet companies, the first one that was spun out of Google, and it aims to understand the problem of aging and to help people live longer and healthier lives. Now, when you look at aging, you realize that it's actually the single largest risk factor for death. And I know that seems kind of funny when you think about it, but it's true for almost every disease that happens after the age of 40, that as you grow older, year after year, the risk from that disease increases exponentially every year. Whether it be diabetes or cardiovascular disease or cancer, all of these increase exponentially. No one knows why that is. Why is it that every year of life after the age of 40 puts us at an increased risk for each of those diseases? And in order to understand that, we really need to study the biological systems that exhibit aging at the molecular level all the way through the systems level and figure out what it is that's causing us to age. Because, I don't think we'll live forever, but maybe we can live longer and healthier by interventions. One of our earliest scientists, Cynthia Kenyon, who came over to Calico from UCSF, showed that with a single gene mutation in the nematode C. elegans, you can extend its lifespan by something like 30 to 50%. And not only does the worm live longer, it lives as if it were a healthy young worm. And it's in terms of reproductive health and movement and so on. So can we do something like that that would allow humans to live healthier? So that would be really cool, but in order to do that, there's a whole lot of understanding that we still need to gain. And in order to do that, we need to gather data about all of those systems, all of which age, yeast age, worms age, flies, mice, humans. What is it that we all have in common at the molecular level? So fortunately, scientists have been able over the last 20 years to devise a whole slew of measurement modalities that allow us to get an understanding, or at least data, regarding systems as they age. And that includes techniques like sequencing and microfluidics at the low level, and imaging, all the way through to things like track devices that track movement and allow us, wearables to track movement and see how systems change as they age. But no human being has the capability to put together data at these different modalities that range all the way from subcellular to entire human populations. All these different modalities that include DNA and RNA and mass spec and imaging and so on, all of the time scales that are involved, from the subcellular scales all the way to the scales of an entire human lifespan. How do you put all these together into a coherent picture of what makes us age and what interventions are the most likely to be successful in slowing that aging process and making it better? So that ability to interpret the data and make use of it really requires a true partnership between the scientists who are collecting and getting intuitions about these processes, and the machine learning people who can help construct models that can synthesize and put the whole thing together. And neither of these communities can be successful on its own. I was one of the fortunate people who entered this field in its very early stages. So I've been working in the field of computational biology since the early 2000s. And as such, whereas you could say that I'm native in the language of machine learning, you could say that I have a fluency in the biological language. And as such, it allows me to work with the scientists at Calico to create a true partnership between those two disciplines and build models that, as I mentioned earlier, is so important to combine the best of both worlds, the best of big data, but also the best of human intuition. Because biology is so complex that I don't think that even with the amounts of data that we're collecting today, we'll be able to reconstruct biology de novo from data alone. You need the data, but you also need the intuition of some of the world's best scientists. And so by working together at a place like Calico, we can get some of those insights as well as some of the enormous amounts of data that are currently being collected, and I'll come back to that later, to really construct an in-depth understanding of the biology of aging, and at the same time, try and predict which interventions might be helpful.
Thank you, Daphne. I feel we should pause. A lot of profound thinking. Hang on to your hats. We're going to jump back to vision. And Fei, just the other day, you were quoted in TechCrunch as saying vision is the killer app of AI. And so what do you mean by that? And what does it mean to democratize AI? And what does that have to do with the cloud?
Yes, so yes, I was actually trying to be provocative, and I stand by it. The quote is that while many people are asking for the killer app of computer vision, I would say the killer vision is the killer app of AI. So let me qualify that by two reasons. The first reason comes from nature. 540 million years ago, a remarkable event happened in animal evolution. For some odd reason, the number of animal species went from very few simple species to an explosive increase of the variety and the types of animals. It was considered the Big Bang of evolution, or the Cambrian explosion. And zoologists were puzzled for many, many decades about why this happened. And recently, a very convincing and prominent theory conjectured it was the onset of eyes, animal vision. When eyes were first developed in animals, suddenly animal life become proactive. There's predators and prey, and the whole evolution just changed. 540 million years later, humans are the most intelligent visual animals. In fact, nature devoted half of our brain for visual processing because of its importance. So that's one thread of one evidence. Another piece of evidence comes from technology and the world we live in. If you look at our internet today, where data is awash, well, YouTube alone sees 300 plus hours of videos uploaded every single minute. And it's estimated more than 80% of the entire cyberspace is in some kind of pixel form. And you look at the sensors, the biggest data form that sensors capture are in some kind of images, whether it's visible spectrum or a spectrum outside of visible lights. From biology labs to hospitals, from self-driving cars to surveillance cameras, everywhere the pixel format, data in pixel format is the most valuable data for consumers and companies. At Cloud, I had the chance to talk to a lot of customers. I have been all about the demand of image recognition, video processing, video analytics. So it's really exciting time for computer vision. Again, it's just similar to speech recognition. Thanks to the progress of deep neural net, vision has really taken off. As a field, have made a lot of progress. In the past 10 years, between 2010 or 7 years to 2017, I would say that the biggest progress in computer vision is the basic perception tasks, object recognition, image tagging, object detection. We already have, you see products coming out of it, Google Photos, pedestrian detection in self-driving cars, and all this. But the next phase in investing in computer vision technology, in my opinion, is really Vision plus X. Vision is so fundamental in communication and language. How do we speak stories? How do we tag and index videos? So the connection and interplay between vision and language is going to be extremely interesting. Then vision in biological sciences, whether we're the throughput of data coming from biology and healthcare and medicine in vision form is phenomenal. And be it radiology or laboratories, and I think there is a huge opportunity for vision to play. And one last example I also want to give is robotics. Vision, speaking as a researcher, there is a lot of excitement now happening in the area of vision and robotics. We've been doing robotics for as long as AI ever existed, but robots are still not where they are. To a large extent, it's because of its primitive perception system, and I think vision can play a huge role. So basically, I do think vision is one of the most important elements of machine intelligence, and also for the transformation of enterprise and companies.
Thank you. Great perspective. And I need to be careful because we're running out of time. So Fernanda, you know, how does vision help visualization, and visualization help machine learning? And maybe to save time, you can from that go into where you see the future of where you can take the visualization.
Sure.
Yeah.
So to piggyback on Fei-Fei's answer here, we have this amazingly sophisticated vision system. We might as well use it to understand what these machines are doing, right? So machine learning runs on tons of data, tons of statistics and probability. Well, it turns out that data visualization can kind of be a secret weapon in trying to understand what's happening. And why do we care? Why should we care? We should care because of a bunch of different reasons. One is interpretability. Can you interpret what's coming out of your models? Second is debuggability. Better understanding what's happening with your models will allow you to then debug them. And then finally, there's also education. Visualization is already playing an important role when it comes to education about machine learning. And I also have a final education piece there that I'm very excited about, which is when we start to understand better, when we use visualization to understand better what these systems are doing, then can we learn from them? Can we become better professionals, better domain experts in whatever? If I'm a doctor, if I'm an architect, whatever it is, how can I learn from these very specific systems and then be better as a professional? Another thing about visualization that I think is really powerful and really important to keep track of is the fact that by using visualization, we're always keeping the human in the loop. Right? And that is huge. And as we build autonomous systems, we want to make sure that they are behaving well. And so visualization can be helpful there. I want to tell you a very quick anecdote about a moment, a scientific moment when visualization showed us something we didn't know before about a machine learning system. So last year, Google deployed its multilingual translate system, right? And it was great. It was this really exciting moment of just putting a ton of different languages in one system and having the system somehow figure out how to translate from every pair of languages. The extra bonus was that it was able to do what is called zero-shot translation, where it was able to translate from pairs of languages it had not necessarily seen before. So one of the fundamental research questions that the experts doing those systems had was, how is the system resolving this space of multilingual data? Is the system creating something that looks kind of like, you know, a model over here for English and a model over here for Spanish and another one for Portuguese? Or is the system doing something very different, where it kind of mixes everything up in the same spaces, and it's maybe learning something about the semantics and the meaning of words, and not necessarily what language it comes from or what language I'm translating to? So what we did is we built a visualization to look into this. And the really exciting point was when we started seeing that we visualized sentences that were being translated into a bunch of different pairs of languages. And the really exciting thing was when we saw clusters of sentences in these different languages show up together. So if I have a sentence that I'm translating from Portuguese to Spanish to English and vice versa, all of those representations showed up clustered together. And then another sentence here with all the clusters of all the languages. And then, so in other words, what did we find out? We found out that the system was not partitioning the space into different languages. The system was coming up with, with a unique representation of those multiple languages. So in other words, we saw the first signs of a universal language, of something that we call interlingua. That was amazing. And so it was almost as if we had ran this multilingual system through an MRI, and we're like, whoa, these are the results. This is the other thing the visualization allowed us to do, was to then look at neighborhoods that didn't look very well resolved, where a little language was kind of hanging out by itself. Those were translations that were not good. They were not high quality. So what that tells us is that the geometry of these spaces is meaningful. And if you have our neighborhood sort of hanging out in the periphery by itself, you might want to look at that. You might want to make sure that you debug your system, right? So these are kind of superpowers that you can have in understanding and making things better, making things work better. And for the future, one of the things I'm really excited about is sort of goes hand in hand with something that Fei I think is a true advocate for, is democratizing AI. Visualization, I think, and other techniques, it's not only visualization, but I truly believe that the more different kinds of people we bring into the fold of ML, the better off we're going to be. Right now, AI still feels very engineering-centric, and I'm really curious what will happen when we bring in designers, UXers, scientists, as we're starting to bring in. What are the different possibilities? What are the different solutions that we haven't even thought about that we can then start exploring?
Thank you. Françoise, I feel like I should ask you, how's data visualization going to help speech recognition? But I also wanted to ask you about, as data gets more complex, you know, we've had all this labeled data for the training models, and we do more personalization. You know, where's the technology going, and what challenges are you excited about?
Yeah, it's actually very interesting. Each time we jump into a new problem in speech recognition, we really have to focus on it. In a sense, you know, when we started working on YouTube Kids, for example, which was a YouTube space for children, we really had to focus on those young voices. They don't speak the same way we do. They don't have the same pitch range. They don't have the same way of chopping words. You know, they take this deep breath and then they have a burst of speech. So we really had to focus on it. And then eventually we found a way of folding back that learning into our generic model so that Google Home, for example, would work with your children as well as it does with you. But Google Home itself was also a new environment where we had to collect new data. And when that data is available to you, then it's easy to fold it into the models and keep retraining. But the first time you want to launch a Google Home device, you don't have it, right? And so we did a lot of simulations, taking data, adding noise of different types, doing different types of reverberation on the data. And indeed, we use massive amounts of data. We transcribe tens of thousands of hours of speech, and then we multiply it with those simulations. If you do the math, it averages to something like, you know, a handful of centuries of speech that we can fold into a model. So it's just massive amounts. And I think it's very interesting to think about how that scales to more problems with different acoustic characteristics, but also to different languages. If I can ask you guys, like, you know, how many of you speak another language than English? Right? You see, all the hands are raising. So we really want to make our technology available to all of you in your own language. And if you think of it, it's a massive problem. How are we going to do that? Are we going to build one recognizer that works for all of you? Are we going to do like we do now, one per language? Well, how about dialects then? And how are we going to do when we have a language that's a fairly small one, small pocket of individuals? So if you ask linguists, they will tell you that there are 6,000, 7,000 languages in the world. They will tell you that there are about 1,000 of them, actually 1,342 they say, that have more than 100,000 speakers. So that's a lot, right? And if we want to really go into deep internationalization and serve all the languages that have big populations on Earth, it's going to require a lot of creativity on the machine learning side to manage to share data among languages, learn from other languages, and so on. So I think it's really exciting, and there is still a ton of work to do in that domain.
I agree. It's super exciting.
Yeah.
Thank you. We're going to go a little over so we have time to hear about the future from Fei-Fei and Daphne. Fei-Fei, what excites you about what's possible going forward?
What excites me about what's possible going forward, let me just say one dimension. I think I genuinely believe AI is one of the driving force of the fourth industrial revolution. It's just the beginning, but it has the potential to transform the way humans live, work, communicate. And one favorite line I heard from a philosopher is, there's no independent machine values. Machine values are human values. So one thing that really excites me is to include the diverse technologists in the field of AI to build the future together, because once we have that diversity of representation in the field of AI technology, we will build the technology that is for the entire humanity, not just a slice of it. So,
Yes, you have a lot of credibility when you say that, Fei-Fei. And Daphne, the intersection of biology and computing and everything else you've done, what?
Yeah. Well, when I look at the progress that machine learning has made over the last 5 to 10 years, and as a longtime AI researcher, if you'd asked me even 5 years ago, will computers be able to caption images without any kind of prior knowledge, just in the same quality that a human would, I would have said, nah, maybe in 20 years. And with the work of Fei-Fei and others, we've been able to reach that milestone way sooner than I would have expected. The reason I moved back to biology from Coursera is because I think we're hitting that knee in the curve in biology. So when you look, for instance, at some of the current predictions, there was a paper that was published in 2015 called Big Data, Astronomical or Genomical. And it looks at the number of human genome sequence, which is a very limited part of biological data that's being captured. And you look at the historical trend, and that amount doubles every 7 months, which makes it about twice as fast as Moore's Law. So if you look at 2025 and you project that line, the number of human genome sequenced by 2025 will be, on a conservative projection, 100 million, and if you look at the historical trends, it'll be 2 billion. 2 billion human genome sequence, and that's just sequence. That doesn't count RNA and proteomes and whole body imaging and cellular imaging. So we're at the cusp of the beginnings, I think, of really understanding what is the most complex system that we have encountered, which is that of a biological system. What is it that makes us alive? What is it that forces us to die? And so I think with that amount of data and the techniques that machine learning has developed and will continue to develop, we have an opportunity to really transform this science in this way. And I'm really excited to be able to bring those two communities together to make that possible.
So there's clearly so much more that we could sit and listen to here. This has just been a phenomenally interesting and inspiring panel. Thank you very much.
Thank you, Diane.